Hello everyone, and today we're going to be talking about particle filters. So before we get into that, I'm going to probably talk a little bit about what we use particle filters for. So a really common application of particle filters in robotics is this thing called localization. So what is localization? And the way to think about localization is you're trying to figure out where your robot is in the world. So what we typically have is some idea of where we start, so an estimate of our initial location. We have some idea of how our state is going to change over time. We have some sensors that are giving us some information about where our state is. And then we have some idea of the world. And through all of that, what we're going to get out is something called a state estimate. So where our robot is in a 3D space. So what that'll actually look like is we typically have something like, oh, here's our x0. So we have this circle that represents our uncertainty within the world. And essentially what we're saying is we're in this circle. We're not sure exactly where in this circle we are. We're probably closer to the center than the outside, but that's really all that we know. And then what we're going to do is we're going to move, and we're going to try to move in this direction. But by doing so, we've increased our uncertainty. Our actuators are not perfect. We have not moved exactly 1 meter forward or 1 meter to the right. We have gotten pretty close, like we did pretty well. But now we have some uncertainty about where we are that has grown. So we have this new state, x1 minus, and this is essentially saying we've not applied our new sensor readings, we've just moved forward, therefore our uncertainty has increased. So then what we're going to do is let's say we get some sensor reading that says, oh, you're in this center point. So we're like, cool, we can shrink our uncertainty. So we're more sure that we're in this little circle. And we get this x1 plus. So we've applied our sensor reading, and now we're in potentially a new state. And then what we're going to do is we're going to move again, because robots like to move. So we're going to move, and we have some increased uncertainty again because we have moved. So we have our x2 minus. And then we're going to get some new sensor reading, and we're going to go, oh, the sensor reading is right there, so it's a little bit more certain that I'm over here. Then we get this x2 plus. And this is essentially the process of localization. You're going to iteratively do this over and over and over again for all time until your robot stops working, which, given our history, is about 5 minutes. So how do we represent this uncertainty about our location? So what we typically do is make this thing called a Gaussian assumption. So what we're going to assume is that there's a lot of things that are going to contribute to our uncertainty. We're just going to assume that they represent some Gaussian that we do know a couple properties about. We're going to know the mean and the variance. So the mean just represents the center. So for this graphic, that would be the direct center of what you're seeing here. And then the variance is kind of those bands that are going out. So what the variance actually means is that we have some probabilistic representation of that we're in this circle or outside of this circle. So in this first circle that you see here that I just highlighted, the probability of us being in that circle is 66%. 66% of the time we will be inside that circle. Now this second circle, we will be inside that circle 95% of the time. So that's pretty good odds, right? But we can also include the third sigma, which is this big circle out here, and there's a 99% chance that we will be inside that circle. So this is how we represent the uncertainty about our state. We usually approximate it by some Gaussian centered at some point, and then we have some variance. And what you're trying to do in state estimation is correctly move the mean, and while maintaining the variance as low as possible. Because this means that we know where our robot is with greater certainty, and the more accurate our mean is, the better. So before we get into localization in a more mathematical sense, let's talk about some notation. So when I first started doing robotics, this is the thing that kind of confused me when I started reading papers. I had no idea what X stood for, or U, or hat, or Z, or whatever. So I'm going to kind of cover some of the common notation that I've seen. Obviously every paper is a little bit different, and they might have different notation or different conventions, but these are the ones that I run into on a frequent basis. So we have X, which represents our robot state. We have U, which represents our robot control. We have Z, which represents a sensor reading. We have some Z hat, which is an estimated sensor reading, which we'll get to in a minute. And we have some X hat, which is a robot state estimate. So oftentimes when you're doing localization, all you're actually seeing is X hat and not X, because you're only estimating the state, you do not know it with complete certainty. So what are we really trying to do with state estimation? Well, there's one way you could look at it and say, well, I want to know what is the most probable state at the current time given all of my prior states for all time, plus every sensor reading I've ever gotten, plus every control I've ever used. So what is my most likely state given everything that has happened to my robot ever for all time? A common word that I'll use is this thing called a prior, and you can essentially think of this as a prior, because that is the prior information I knew when I came to solve this problem. The first component of localization is this thing called a sensor model. So the sensor model essentially gives us what is the expected sensor reading. So what should my sensor tell me if I'm at a certain state? And you can frame this in a probabilistic sense. So we have some z hat, because remember it's an estimate, it's not the actual sensor reading. Given some function h, so h is a function that goes from our state x to our sensor reading z, and then you have some noise epsilon. So this noise is going to be that same stochastic noise we've talked about. We don't really know exactly what it is. We'll probably assume it's Gaussian at some point. You don't know exactly what that noise will be, but you'll get something that's pretty close. So you can think of the sensor model as kind of giving you what is the probability of a sensor reading given some state. So remember how we talked about normal distributions. And this is the notation that you'll see from our normal distribution. This is also called the Gaussian distribution, and you'll see me use the terms interchangeably. So we have some epsilon that comes from a Gaussian distribution with some mean and some variance. So this is the actual probability density function of that Gaussian. And don't worry about this equation, it's super complicated. I have to look it up every time I see it. But essentially the thing to think about is you have some mean which centers your Gaussian, which looks like this, and then you have your variance, which essentially represents how far out the Gaussian is reaching. So the second component of a particle filter is this thing called a motion model. And the motion model gives us what is the next state given my previous state and my previous control. This is also called dynamics. As you can see, that's mathematically written out here. So we have f, which is our dynamics function, which takes in x and u and outputs a new state. And essentially what you're getting is some probabilistic representation of what is the probability of some state given that I have the previous state and the current control. And again, this is corrupted by some noise w, because we're always going to have a little bit of noise. So let's actually go into a derivation of what we're looking at. So remember that we started off with this idea of what is the most probable state given all of my previous sensor readings and all of my previous controls. So remember we had this idea of what is the most probable state trajectory given my previous sensor readings and our previous controls. So we can write that out like this. And then what we can do, so using the rules of conditional probability, we can split it like this, where you take out this z sub t from the whole large z sub t. And this is essentially saying the same thing. It's more of a notation thing, because as you can see, x0 to t is still conditional on all the same values. Then we can use this slightly different form of Bayes' rule. What we're going to do is we're going to have this conditional z, and it's going to remain conditional on the entire time. Remember, Bayes' rule allows us to write what is the probability of x given y, as probability of y given x, plus some other terms. And this is the exact same equation, just if we leave it always conditioned on z. So you can use a slightly different formulation of Bayes' rule, as you can see here. And remember what Bayes' rule allows us to do is rewrite conditional probabilities in the reverse order. So I can say what is the probability of x given y as the probability of y given x, plus some other values. So we're going to use this application of Bayes' rule onto this top equation here. And what that's going to do is going to allow us to rewrite things like what is the probability of the state given the sensor readings, as what is the probability of the sensor readings given the state. And we're going to do this around these values here will remain conditional on, so this will be our z, and then we're going to flip the x and y, where this represents our x and this represents our y. So we write out that form of Bayes' rules, you get this equation down here. The next thing we're going to do is we're going to talk about proportional. So we're going to assume things are proportional to. That's what this symbol is saying. The reason we're doing that is because this thing on the bottom is hard to define. What is the probability of a sensor reading given prior sensor readings and prior controls? We don't really know how to calculate that. It also doesn't really make a lot of sense. So all we can say is all we're trying to do is figure out what the most probable state is. So the most probable state, all it needs to be is proportional to. It doesn't need to be the exact value. We don't need to compute what the probability of a state is. We just need to figure out what is the most probable state. Slightly different formulation, and that allows us to do this trick where we say it's proportional to, and we never actually have to calculate out this denominator. So you represent the denominator by this thing called eta, and you'll see this convention a lot, and then people will say it's proportional to through this symbol here. So now we have this new equation, which has less terms and is a little bit simpler. So now if we rewrite that, remember for what we're trying to do, is we started off here, we have what is the probability of the state trajectory given some prior sensor readings and prior controls. We're going to say that is proportional to the equation we have on the right. So next we're going to use this thing called the Markov property. So before we had this giant conditional. It's conditioned on this giant history of states. But do we really need that? What the Markov assumption says is that we don't actually need that. Essentially, the values at t only depend on t minus 1. we don't need the entire history to say something about t. We only need the prior state. So using the Markov property, what we can say is this giant conditional here only depends on the prior state. My current sensor reading only depends on that state at that time the sensor reading was taken. The camera image at now doesn't depend on what I was doing 10 hours ago. The two aren't related. So we can use that to simplify our equation. The next step we're going to do is here, what we can do is we can split this into x of t and then x of 0 to t minus 1. So essentially what the current thing is that I care about and then everything else. So we can use the rules of conditional probability to do this. And that's this step. And then, as you can see here, we can reapply our Markov property in a different context and say that my current state, x of t, only depends on my prior state, x of t minus 1, and my current control. And then we have this probability here that just represents all of history. So finally writing out those equations, remember what we have here is, what is the probability of the sensor reading given our current state? What is the probability of the current state given the prior state and the current control? And then what is all this history? Plus everything else that ever happened ever. So we can do kind of a little trick in probability and just marginalize out. So we just sum across all history, and then we get this representation, which is what is the probability of my state given everything can just be written as this simple equation. So as I say simple equation, I'm kind of hiding a lot of things here. This integral is on all history ever. So often we can't compute this, or this is very difficult to compute. Usually you just can't. So as I say, it is a great equation, but we don't have a closed form solution. We can't compute this. So what do we need to do? We're going to do the thing that we often do in robotics, and we're just going to approximate it. Because we always just do approximations in robotics. So what we're going to do is approximate with a bunch of discrete guesses. And that is what a particle filter is doing. It's going to approximate some probability distribution based on a bunch of discrete guesses. So let's say I have a bunch of guesses. Let's say I have a robot in a 2D plane, and my robot could be anywhere on this 2D plane. So given that I have a bunch of guesses, what I can do is these particle filter steps here. So the first thing I'm going to do is I'm going to take my guesses and I'm going to move them based on how I think they should move. So I have some motion model there. And then I'm going to say, okay, now that I've moved them, what is the most likely state given the sensor reading that I have? And that is going to use our sensor model. And then what we're going to do is we're going to change our guesses to be more likely. So what does this really look like? So let's say we have our little robot, we have some representation of how it's going to move, we have some plane that represents where our 2D robot could be, and we have all these little dots. And these dots represent possible states our robot could be in. So then what I'm going to do is our robot is going to drive forward. So if the robot drives forward, that means I'm going to take every particle and drive it forward. Now I haven't done a great job of representing the orientation, but it doesn't really matter. So all these robots, all these little guesses of our robots will move in some direction based on their orientation. So now that I've done that, I can move to the next step. So now I've moved my particles, they moved around the screen, and then what we can do is we have this green dot. This is essentially a sensor reading saying that I think my robot is here based on the sensor reading that I just got. So now that I have all these guesses, I can say, oh, which guess is more likely than others? So you'd probably say that this one, or this one, or this one, or this one is much more likely than any of the others. So that's what we're going to say. And since these guesses are more likely, we want to use those moving forward. So the next thing that we're going to do is resample. So essentially I want to remove particles that have low probability and add particles that have high probability. So typically the way you do this is you remove particles with low probability, and then you pick particles with high probability with replacement. And essentially what that means is I can have multiple particles that are identical, at least for a little bit. But remember, when we do our motion model, we're going to move them slightly differently. So now I have things that look like this, and after I move those particles, I get some representation that looks like this, and we can probably guess that our robot is somewhere in the center of these particles. And that's the high-level idea of how a particle filter works. So this is the actual algorithm for a particle filter, if I was to write it out. And this is the notation you'll see a lot of times when I talk about algorithm. A lot of people use this same notation of what I'm doing here. So the way to kind of break this down is you have some given. So these are things that aren't going to change through the algorithm usually. So I'm given some things. So these are a lot of times called hyperparameters, or things that you know before you do the algorithm. And then I'm going to have some input. And these are going to be like, what's my robot's state, or what is its control? and then I'm going to return what those values are. So think of it kind of like a function. So for a particle filter, what I'm going to do is for every particle, xi, in this set x, capital X, which represents our set of all particles, I'm going to move it based on my motion model. If you remember the equation from earlier, as you can see here. And then I'm going to weight those particles based on their probability. The most likely particle will have the highest weight, and the least likely particle will have the lowest weight. And then what I'm going to do is I'm going to resample them. And that's what you see in this step here. So going through this for loop, what I'm going to do is I'm going to resample from that x based on their probability, and then I'm going to add that new particle to a new set of particles. And at the end of this particle filter, I'm going to return my new set of particles. And if you were to use these, you could figure out the state estimate. So in summary, particle filters are really nice. They're pretty easy to understand, and they're pretty easy to implement, and their computation time just depends on the number of particles. So as you increase the number of particles, your particle filter will run slower, and as you decrease it, it will run faster. And you also have a free choice of motion and sensor model. While this doesn't make a lot of sense now, it will later in the course when we talk about common filters. There are a lot of assumptions that we'll be using when we do a different derivation, and these don't exist in the particle filter. So you can kind of do whatever you want, and it might work and it might not, but there's nothing theoretically saying that you can't.